So welcome everyone for today's Quantum Spacetime seminar. Today we are very happy to have Ahmed Almheiri from New York University Abu Dhabi, and he's going to tell us about TTbar and the black hole interior. Over to you, Ahmed.
Hi, thanks a lot, Abhijit. Thanks for the invitation to speak, and thanks for being flexible in arranging this this talk. Hopefully, in the future, I can come visit in person. Okay, so I'm going to tell you about an idea connecting TTbar and the black hole interior. It's based on work in progress with my postdoc, Simon Lin, and my graduate student, Shadi Ali Ahmed. Okay, so TTbar is somewhat of an old subject, and as only recently got into it and started learning about it. So I'm essentially just playing catch up. So I'm just looking for my notes. Okay, and the new thing here is going to be connecting the old story of TTbar to the black hole interior. There have been some works in this direction. As far as I know, our work is original in that regard. Okay, let me start by motivating why am I doing this. Let me recall a major hurdle in understanding the black hole interior. Okay, so ADS-CFT has been great, but it taught us mostly about black holes from the outside, and not a whole lot about the inside. What it tells us about the interior is usually just extensions or continuations from the outside going in. What is missing is a non-perturbatively, or rather, a non-perturbative definition for interior operators. So if let's see. And in the context of ADS-CFT, it's how to define interior operators non-perturbatively from the boundary perspective. That is something that is still missing. Embarrassingly, in ADS-CFT, the only non-perturbatively defined operators are actually just those near the boundary, namely those that are given by the extrapolate dictionary. So you take your bulk fields, phi, let's say some scalar field, and you multiply it by some rescaling factor, and that's meant to define for you a bulk operator O. Okay. As far as I know, this is the only non-perturbative statement in defining ADS-CFT. The issue with trying to get to the interior is, well, there's a lot of space between the boundary and the interior, and so a lot of space where the metric can do whatever it wants to do. Spacetime can do whatever it wants to do. You have no guarantees about whether about what happens as you go from the boundary into the interior. You can have wormholes, and over here you can have spacetime just ending suddenly. It's not clear. Usually in a theory of gravity, the way you set things up is, at least in this context of ADS-CFT, is by imposing boundary conditions. So the only place where you know exactly what your spacetime is doing is near the boundary, and as you go into the bulk, there are no guarantees.
So Ahmed, that's true even a little bit into the bulk, even before you reach the interior of the black hole, right?
Of course. It's even worse in the interior, but your point is valid. Okay. Now, the thing that I want to say is that given that it's the boundary where it seems like we have control, then perhaps we need to engineer a way to move that boundary into the interior. So that's maybe one way to be able to define interior operators non-perturbatively. A first step towards shrinking the distance between the boundary and the interior was this proposal of McGuff, Mazet, and Verlinde, who said that if you start with a holographic CFT, let me first write down the names, McGuff, Mazet, and Verlinde, who said that if you have a holographic CFT and then you construct a family of so-called TTbar, let me put a TTbar, deformed cousins, let's say, a la Damologikov and Smirnov, defined through d lambda S HQFT E squared X ET bar. So this is Damologikov and Smirnov. That if you define this family of deformations of the holographic CFT, as you tune this parameter lambda that scans across this family, what that's meant to be dual to is moving the boundary into the bulk. So this parameter lambda roughly is like 1 over r. Turns out to be 1 over r to some positive power. Okay. Okay. But this proposal of McGuff, Mazet, and Verlinde, so the MMV, that only tells you how to go up to the horizon. It doesn't tell you about anything else. And the thing that I'm going to be talking about is how to modify their proposal such that such that you can take the location of the boundary and place it inside the interior. And I will discuss why I'm drawing these slices as space-like slices. That's going to be an outcome that we'll see later. So again, just to recap, MMV tell you how to evolve to the horizon. And what I'm going to do is to tell you how to start from where they ended and push into the interior.
Sorry, could you just say a little bit more specifically what the MMV proposal was? So what are the boundary conditions? I mean, how is this theory with the finite cutoff defined?
Yeah, I will review all of that. Okay, so far this is just a cartoon.
Great.
Okay. All right, so the outline of my talk is the following. So outline, let me do the next page. So I will start on the boundary. I will give a review of TTbar. And then give a prescription for applying a sequence of TTbar-like flows. So the sequence was meant to refer in that picture that we just saw, that the first step would be to evolve from the boundary to the horizon, and then the second step would be to start from the horizon and evolve in. Obviously, that's the bulk interpretation of a boundary prescription that I will describe. Then I will describe this process in the bulk, And in particular, I'm going to talk about what Shiraz wanted, what are the gravity path integral boundary conditions that implement this flow or flows. These flows, and in particular, what are the boundary conditions for the interior? Okay. So that's the outline. Okay, so let's start with the review of TTbar. So what we mean by TTbar is really the, at least in 2 dimensions, yeah, I should have said that. I will work in the context where my, in the original context in which TTbar was defined, which was 2D conformal field theories. So TTbar is the operator, which is just a determinant of the stress tensor, which in holomorphic coordinates you can write as T times T bar minus theta squared, where theta is the trace of TAB. Okay. This, let's see. This operator, this TTbar operator, is a Lorentz invariant operator, since it's the determinant of the stress tensor. And the reason why it's so interesting is because Zamolodchikov showed that if you take its expectation value in any primary state, then you find that it factorizes. Okay. Using this property,
this is in a CFT or a general QFT?
In a general QFT.
Okay. What does primary state mean then in the general QFT?
This is well, okay. I think it's true in a general QFT, although what I'm going to use is in QFTs that are constructed by deforming CFTs for now.
Okay.
And what I mean by primary, I mean those states that start as primary when it was CFT. Does that make sense?
Thanks.
Yeah.
Perfect.
Okay. Using this property, Zamolodchikov, well, using this operator rather, Zamolodchikov and Smirnov defined a family of deformed theories, or let me write it as deformed actions, defined by the following operator equation. Or maybe let me just put lambda here. So you take your favorite CFT and you take its action, and you declare that that action has some lambda dependence and satisfies this flow equation. That's how you define it. And what they showed is that you can solve this you can solve for this flow, assuming you have the boundary conditions that at lambda equals 0, the action is the action of a conformal field theory. Okay, this is very important. All right.
So the action, action is on For instance, on a torus, the action is a function of manifold parameters, like the torus parameters.
Yeah, let's say on the torus, yes. I don't think it's important. Rather, I think they want to define this generally. So you can consider your theory on the torus, on the cylinder, etc., and it's meant to apply case by case.
Okay, thank you.
Yeah.
Ahmed,
Okay.
Yeah, so this ace of lambda, is that a classical action or is it an effective action? I mean, is that a quantum thing that you wrote, del lambda, S lambda equal to integral of TTbar?
Yeah, I think at the let's see. My understanding was that this is meant to be an operator equation. And then, but I will only consider it. I will consider expectation values of this equation. I don't know if that addresses what you're asking about.
I thought by S you meant log of partition function. If that's not correct.
That's not correct. It's really this.
So how do you define TTbar of lambda? I also thought somehow that it's the expectation value of TTbar when you insert TTbar in the path integral, but that's not the case.
Well, usually people mean that they just, at any value of lambda, you deform the action of the path integral by the TTbar operator at that particular value of lambda. So at that value of lambda, one assumes that there's a stress tensor and one writes down the TTbar operator and you add that to the action with a small delta lambda, right? Is this, I think that's probably what Ahmed meant. Is this right?
But what is your definition of the action? Is it just log of the partition function, or is it something more fine-grained? Is it the thing that's inside the integral?
I think it's the thing that's inside the integral, the thing that sits in the exponential.
Yeah.
Of the path integral.
But what do you mean by T?
Well, I mean, I think that standardly people mean del S by del G, right?
Yes. Okay.
Yeah. But sorry, I mean, you may have you should say what you had.
I think that's essentially what I mean. So you first give me S lambda, which is some expression in terms of all the fields in the theory, and then you define your T's, your T as ds by d whatever AB, GAB, etc. And then you construct this equation from what you obtain here.
Sorry, but when you say you can solve this starting with lambda equals 0, when you're solving it, you're solving the expectation value of this equation?
Exactly. So the thing that I'm going to use is expectation values. So in the following way, so this equation leads to two things. One is that if you vary both sides with respect to gamma AB, and I should note here that I'm going to take expectation values, then you get d lambda of the expectation value of TAB at lambda is equal to gamma AB expectation value of TTbar at lambda, okay, where this is some just background metric. Which we're going to set to be just a standard flat metric. And two, because lambda is the only scale in the problem, differentiating with respect to lambda is like applying an infinitesimal scale transformation. And the the charge of this that generates this transformation is just a trace of the stress tensor, and so you expect, and so what you get is that this equation here also gives you the second equation, TTbar lambda. Okay, this is known as the trace flow equation. Okay, so there were two, again, just to recap, there are two equations that we can get governing the evolution of the stress tensor as a function of lambda from this single equation that define the flow. Okay. If you
if you have a
go on.
Just question. Yeah, if you have a CFT on some space with some metric and another metric which is wide equivalent to it, then you know the partition how the partition functions are related because of this Y factor.
Mm-hmm.
There's some similar equation for this TTbar deformed theory also. Are they equivalent in some sense up to while while rescaling them?
I'm not sure, just because you don't have that you don't have that symmetry once you're you don't have that property once you're away from lambda equals 0.
Okay.
So
yeah, I mean that exact property may not be there, but I was wondering whether there could be some deformation of that.
Yeah, that's a good question. I'm sure people have thought about this. I don't know, unfortunately.
Thank you.
Okay. Now, if you combine these two equations, you can get the following equation that governs how the spectrum of the theory depends on lambda. So by using factorization plus taking the expectation value to be in a primary state, and let's look at the TTT component, and that gives you the following equation: d lambda E is equal to E squared minus J squared divided by 1/2 minus 2 lambda E. Okay, so that's the flow equation that one gets for every energy eigenstate, or rather any E. Okay. The solution of this equation is well, let me first plot it. It's a first order differential equation. It needs an initial condition. One starts with the energy, let's say E naught. Sometimes I will call this the seed energy. And then as a function of lambda, this energy grows up until some point, and then it goes off to the complex plane. It's a critical lambda C. And you can see this more explicitly by looking at the what does the solution actually look like? So it's 1/4 lambda, 1 minus square root 1 minus 8 lambda E naught plus 16 lambda squared J squared. Okay, and this critical lambda is where this thing is equal to 0. So it's a function of E naught and J squared. Okay, beyond lambda. Sorry?
There's no central charge in this formula?
There is no central charge in this formula, correct.
Right.
And so at this critical energy, at this critical lambda, sorry, but the critical lambda is energy dependent. Is this right?
Exactly.
Okay. Yeah.
Yes, it is energy dependent. So in particular, at any non-zero lambda, some energies have complexified, right? Because if you focus, let's say, on the j equals 0 situation, then for j equals 0, this is just 1/8 E naught. Okay. Okay. So I will not talk about these, or rather, I will not talk much about these complex energies, because the thing that I'm going to try to do is to give a prescription to avoid them. Okay? And the prescription is going to be the following.
Sorry, one quick question. So the highest real energy you can get is 1/4 lambda. Is that right?
Correct. Yes. Exactly. So this is like 2 E naught. Yes. 1/4 lambda.
And so lambda, so 1/4 lambda should be thought of as roughly an energy scale cutoff in your theory. Or not?
Yes. That's right. That's one interpretation.
Okay, fine.
Yeah. Okay. Okay, so what am I going to do? So I want to give a prescription. That avoids the complexification. But I can't do that for all energies. I'm going to do it for one energy. Okay, so I'm going to define a prescription that for at least one energy, it completely avoids this complexification. So, okay, so here's what I'm going to do. So step number 1, well, just pick E naught. So you first decide on E naught that you want. And for now, I'm going to talk about the case where angular momentum is equal to 0. Okay. Then I'm going to imagine evolving from lambda equal to 0 up to lambda equals lambda critical, which is 1/8 E naught, which is what we just said. And then at step number 3, now the new thing is that once I get to this lambda critical, I'm going to change the deformation going forward to TTbar plus a cosmological constant term that depends on lambda. So this 1/lambda squared. And so this modifies the differential equation for the energy. For example, the lambda E becomes E squared plus 1/lambda squared divided by 1/2 minus 2 lambda E. Okay, so now we have this new term here. I should say that deforming the TTbar prescription by adding a cosmological constant term has been considered previously by other groups, including Eva Silverstein, and I don't know if Onkar was on one of those papers or not. Yeah, okay. So this is very similar, but but for some reason we have, I still don't understand the key difference, but we get different results. Okay, let's see, where was I going to go? Okay, anyways, so we deform the energy, and we get so we deform the deformation, we get a new differential equation for the energy. We can then solve it, and the solution we get is actually following: E lambda equals 1/4 lambda 1 plus minus square root lambda c minus 1, where c here is an integration constant. And this is also a choice. It's you can think of this also as determined by boundary conditions.
And there was I mean, if you just had one shot added a cosmological constant to a quantum field theory, that's sort of trivial, right? It doesn't do much. But I suppose that this does something, because at the next shot, it changes your TTbar deformation.
Yes.
By a T plus something, T bar plus something, and then that's non-trivial. That's why it gives you some non-trivial change. Is that right?
I think that's one way to think about it. Well, let's see.
Because let's say at step 1, it changes T by like something proportional to metric. And then at step 2, the TT bar deformation now is T plus that change into T bar plus that change, which is non-trivial.
Yes, exactly. Yes, okay. yes. Okay. Let's see. Okay, so this is.
Sorry.
Go ahead.
How did you pick the minus sign first in the first discussion?
So good. I will explain how to fix all of these. Okay. But first, let me say that if you that the actual answer for the energy actually has an overall minus sign here. Okay. So I have 3 things to explain to you. One is, or rather 2 things. Let's say 3. What is the value of C? Which plus minus here do we get? And what's up with this overall minus sign? Okay. Let's keep this one to the end, or last. Okay. And for now, I want you. Sorry.
No, I mean, in the previous relation, the square root had a minus sign, right? In the standard deformation.
Correct.
Yeah, I was asking about that. Maybe.
Yes.
Okay.
I will do that right now. So, so the previous case was 1/4 lambda, 1 minus square root 1 minus 8 lambda E naught. And now what we have is E is equal to the same thing, 1/4 lambda, 1 plus minus square root 1 minus lambda C minus 1. And we are matching at lambda equals 1/8 E naught. Okay? At 1/8 E naught, first of all, let's impose continuity. This implies that C has to be equal to 8 E naught. Okay. So if you remember the plot, the energy as a function of lambda, it grew up to some point. And now what I'm saying is that as I continue to evolve with this new deformation, I wanted to start from that point and then go somewhere. Okay, that fixes C to be 8 E naught. Now the question is, what fixes the sign? Which is Abhijit's question. Because so I'm going to replace this C with 8 E naught. If we just fix our, if we keep our focus just on the flow of this particular energy E naught, then nothing fixes the sign, right? Because this term is zero at both terms are zero at lambda equals lambda C. However, if you impose that the flow is continuous for all energies, not just for E naught, then that will fix the sign. So what do I mean? So imagine that you follow the prescription that I just described that was tailored particularly for E naught, but you apply it for any initial energy, okay? But you do the switch at a particular lambda critical, okay? So it's a fixed lambda critical. So you can define a E of, well, what I'm writing down right now is the solution of the energy, sorry, what is this? Let me call this E. Oh yeah, so E naught prime, E naught. This is the solution you get from deforming past lambda critical, but for any seed energy E naught prime. Yeah, so I hope that was well, maybe that wasn't so clear. Maybe I can ask Abhijit. So the statement is again that we by demanding continuity for the flows for any seed energy.
I mean, a priori, it's not clear that there is a solution. Because the freedom is only 2 signs, but the condition is so many. I guess it just works.
Let's see.
So you're flowing and flowing. So you flow all energies up to some point, and then flow all energies away. But according to the new.
No, but the new
will some new differential equation. But you apply it to the all energies.
One constant and one condition. So should be okay.
I mean, you should be able to find the right? Your rule is that you start with this energy, you flow up to this point, and then you, for the next flow, you just take a new rule. Should be a solution.
But he fixed this C, right? From that. He was fixed by matching, right?
But
yeah, C was fixed by matching here.
At one point. Then
just matching one energy, but all energies should match, right? Because you're just flowing and flowing.
yeah.
Yeah. If you pick the other sign, the plus sign, then you'll find that that there's a jump in the energy at this step. So
I mean, even at E naught.
Can you say that again?
Not at enough, not at zero.
Yeah, that was 0. Okay. Okay.
Yeah. The
Sorry.
yes, Onkar.
Can I ask?
So you flow only to 1/8 E naught. It's irrespective of this E naught prime that you started with.
Correct.
Right. So it couldn't already be true that it's going imaginary even before you hit 1/8 E naught.
Correct. It could have already gone imaginary, but I'm demanding continuity irrespective of that.
I see.
Yeah.
Okay.
Okay. All right. Now let me explain this minus sign that I claimed was there, but I'm ignoring, and let me explain why. So this has to do with some of the peculiar properties of TTbar. In Lorentzian signature, TTbar deformed theories, if you pick the sign that corresponds to the one relevant for holography, it causes the opening up of the light cone. So light cone broadening.
Sorry, I was spacing out. What causes light cone broadening? Could you say that again?
Yeah, TTbar deformation.
Okay.
A TTbar deformed theory with lambda greater than 0, which is the holographic sign, let's say, the holographic sign, let's say. It causes this phenomenon of light cone broadening.
On the boundary.
On the boundary, yes, yes.
So it violates causality.
That's not obvious, but in the yeah, let me not comment on that, but let me comment on something else. So the statement is that as lambda goes to well, for lambda greater than 0, for lambda greater than 0 but less than lambda critical, then your light cone opens up. Okay, and the way that this happens is that there's a way of thinking of the TTbar deformation as performing a field-dependent coordinate transformation, a coordinate transformation that depends on the flow parameter and the value of the stress energy tensor. So suppose I have a deformed theory, which I define on this metric, du dv. So I'm going to call these the deformed theory coordinates. There's a way of expressing these coordinates in terms of the original coordinates of the undeformed theory. And it looks something like this: dx plus lambda t yy dy. My x and y are light cone coordinates, but of the undeformed theory, where du is meant to map to this and dv is meant to map to that. So this is undeformed, or rather undeformed coordinates. And if you look at the time component of this metric, it roughly speaking has this form. So you have some f lambda dt squared plus dot dot dot. Let's ignore the dot dot dots. And f lambda is less than 1 for lambda greater than 0. Okay, and this is one way to think of or to describe this broadening of the light cone. Okay, and in particular, f of lambda goes to 0 as lambda goes to lambda critical. Okay, all right. So this is the first point. The second point is that as when lambda is greater than lambda c, f lambda changes.
Lambda c was defined once you fixed a particular energy, right?
Correct.
Well, so then I can't understand how something as, intrinsic as a light cone depends on a particular energy. Sorry, yeah.
So there's an energy here.
Energy when?
There's an energy right here. This is the stress tensor. The coordinate transformation between the undeformed coordinates and the deformed coordinates depends on the stress energy tensor.
Okay. So I'm sorry, perhaps you don't want to address this, but let me ask again. If I just take in the original coordinates and I compute a commutator of two operators outside the light cone, in the presence of the TTbar definition, is that zero or not?
I don't know. Naively, it looks like it's not zero.
And then the question of up to where it's not zero is a question that is sort of shouldn't require specification of an energy.
Yes, and it's
so then.
Yeah, go on.
So I don't understand how your light cone depends on the energy. Sorry.
Yeah. All I can say is that these are good questions, but I don't have a good answer to them right now.
Okay.
And just given the time constraint, then maybe I should keep going because I'm also teaching after this. I'm sorry.
Yeah.
Yeah. Okay. So, but that's a good question. I'm sure somebody must have studied it. The second point I wanted to make regarding this point is that f lambda changes sign. Okay, so there's a signature change. In particular, if you start with a Euclidean theory, so if you start with the Euclidean theory with some inverse temperature beta becomes negative. Okay, and this mistake of this overall sign is just the following observation, that essentially that remember the formula for the energy or expectation value of the Hamiltonian is minus d beta e to the minus beta h, and the mistake that we made, the thing that gives the overall minus sign, is we essentially what we did was we did the derivative with respect to the magnitude of beta of e to the magnitude of beta h. And this is what gave us the overall minus sign. Okay. All right. Yeah. So that's the origin of the overall minus sign. And so if you can correct for this and you can remove that overall minus sign. I just wanted to mention this just for full disclosure. Okay. Okay. And in the book, there's going to be an interpretation of this signature change, which is related to the fact that the space-like slices, or rather that the boundary, which started out time-like outside, became space-like as you went into the interior. Okay, so that's everything I wanted to say regarding the boundary. Now I'm going to start talking about the bulk.
Sorry, can you flash your expression for lambda c?
Can I what, sorry?
Lambda c, can you say what lambda c was again? Can you remind?
Yeah, lambda critical was 1/8 E naught.
So everything is, all this discussion is dependent on that choice of E naught?
Yes.
Okay.
Yes. So right now we're only talking about the properties of a particular energy eigenstate and its flow. From the bulk perspective, we're going to think of this as, I'm going to use semi-classical gravity path integral techniques. And so when I say a path integral with a fixed E naught, it's going to end up meaning like a microcanonical ensemble. Okay. All right. So now let's talk.
Is the state dependence? Can I think of this as state dependence?
I mean, it is a state dependence, but that's a very loaded term. So I'm not sure if you're trying to make a connection to the other contexts or not.
Yeah, I was thinking of like Papadodimas Raju, that kind of thing. That it depends on. your creation of the interior of the black hole depends on what state you're working in, roughly. At least the energy of that state.
Yeah, let's say yes for now. Okay. All right. So from the boundary perspective, we had the input was E naught and lambda. So we gave a prescription for how to do some flow, but the input ultimately was the initial seed energy and lambda, which is how much you flowed. Okay. The question is from the bulk perspective, what is the analogous input? Okay.
I'm just so this prescription of these combined flows, has it made all the energies real for all lambda?
No. What it has done is that it guaranteed that one E naught, one energy, remains real for all E lambda.
Okay, and all the energies below it also can turn complex, above it also can turn complex, or what?
I think the ones below most likely remain. Actually, I don't. Let me see what happens to the ones below. We can maybe look at the equation. This is the equation, and the ones below also become complex. No, they don't. They don't because this thing, oops. So this thing is greater than 0 for the energies below.
Okay.
And so for arbitrarily large lambda, this stays real.
Okay.
But the energies above it stays real, right? Because for the energies above E naught, because they would get complex even later, right? Because they would get complex it.
I think some of the energies above. Let me see. I think some of them
already at lambda C, the energies are complex.
Yeah, those are already complex at lambda C, and the question is whether they stay complex or whether there's some more, like whether they go back to becoming real or not. I'm not sure.
Okay.
Everything should be answered by this equation, but I just want to keep going. Okay. So the question I want to answer is what are E naught and lambda in the bulk? Okay. And the setting I'm going to study will be JT gravity, but viewed as embedded in 3-dimensional gravity plus cosmological constant. I will focus on pure gravity. So I will only study or the only fields that I have are G and phi, G mu nu and phi. The embedding of the JT fields in 3 dimensions is going to be the following. So we have some 2-dimensional metric plus phi squared d theta squared. All right. Let's talk about different candidate bulk energies that can correspond to E naught. The first bulk energy is something I'm going to call, I think this is the right term for it, the Hawking mass. M. And it is something that you can extract from the ADM formalism in the following way. So imagine you slice your space, you have some slicing of your space-time. Here's T, and you have R as the coordinate along Cauchy slices. And this Hawking mass can be defined generally, I think, rather for general general dimensions, assuming you have spherical symmetry. Okay. In that case, when you have spherical symmetry in higher dimensions, or in JT gravity, which is already spherically symmetric, which is that notion is not there. You find that there's a linear combination of your Hamiltonian constraint and your momentum constraint. Pi here refers to the conjugate momentum of the metric. This thing is equal to ER phi squared minus G mu nu d mu phi d nu phi. And by the constraints, this thing is equal to 0. So through these constraints, one identifies a quantity that is constant along these Cauchy slices, which is what I mean by which is the quantity that I'm defining as m, quote unquote, the Hawking mass. And I should say that it is equal to the ADM mass. This is a kind of Gauss law thing happening. In terms of specific components, you can decompose your dilaton in terms of derivatives, at least the derivatives of the dilaton, as those parallel to the Cauchy slices and those orthogonal. This quantity has appeared recently in constraints in a paper of Ronak and Aaron Wall, when trying to define I think it was an entropy bound. The way that they like to think about this quantity m is that you can write it as, if you think of phi as the area of the higher dimensional and the higher dimensional codimension 2 surface, then it's like area squared of 1 minus g plus minus the expansions, theta plus and theta minus. Okay. Okay, so the upshot here is that there's a quantity that's constant along Cauchy slices, and it's equal to the ADM mass, and it has this form. Another notion of energy that one can define is the quasi-local or Brown-York energy. And it's defined in the usual way by applying basically the boundary definition of stress energy to the action, to the on-shell action, and where this gamma TT is the induced metric on a fixed R slice. So here we imagine here's your slicing of your space-time, and here's a constant R slice. Gamma TT lives here. Okay, so that's the definition of Brown-York energy. This is usually defined in the context of imposing Dirichlet boundary conditions at some fixed R, where you have control over varying, taking derivatives with respect to the metric. If you evaluate this quantity in JT gravity, it's equal to the following. So the Brown-York, gamma TT, phi minus E n tilde phi, where n tilde is the normal orthogonal to the boundary. Okay, so normal fixed R. Okay, this is the answer for the energy in JT gravity. But something we need to keep in mind is that the energy that we care about ultimately should be three-dimensional energies, because we are trying to match to the TTbar holography between 3D gravity and two-dimensional boundary, which means we need which means we need to that consideration has to be taken into account when you renormalize to get boundary quantities. Let me be a bit more explicit. So the boundary metric is ds squared is minus dt squared plus d theta squared, while the induced metric from how JT gravity is embedded in higher dimensions is minus gamma tt dt squared plus phi squared d theta squared. The fact that now the way you renormalize from boundary from the bulk from the induced metric to the boundary metric is you first express the induced metric as an overall conformal factor times the physical boundary metric. So here,
we're doing 3D. Sorry for the ignorance of the question, but where is this JT gravity coming from? We're doing 3D gravity. How did you get JT gravity, sir?
I was imagining that I did this decomposition.
Oh, okay. And nothing depends on theta?
Nothing depends on theta.
Okay.
That's, yeah. Okay. I think sort of long story short here is that there is a there's a mismatch between the fact that the metric components here do not align in the same way as they do in the boundary tells you that at least one of these coordinates is not quite is mismatched from the bulk physical coordinate. Namely, I'm just going to now just state it as a claim that that the physical boundary time is related to the bulk coordinate t in the following way. Which ensures that you can write this metric as phi squared minus dt boundary squared plus d theta squared. Okay, this is probably just a technical thing that you need to take into account. This redefinition of the notion of time changes the expression for this Brown-York energy expression. So the Brown-York energy expression renormalized to give you a boundary notion of energy ends up becoming phi times phi minus dn tilde phi. So this change in change in the definition of time between the bulk and the boundary replaces the gamma tt with this phi. Okay, so the upshot here is that there's a second notion of energy, which is the Brown-York energy, which, when appropriately renormalized, gives you this expression. That should be the takeaway from this part.
So, Ahmed, he thought of as some sort of an angular energy coming from some angular deficit.
Sorry, what is meant to be an energy from a deficit?
I mean, if you have some sort of a mass in 3D gravity, then it has some angular deficit around it, right?
Yes. Yes. This is supposed to reproduce that. but just from this other
That is-
perspective.
That is basically that formula, right?
Yes.
And then dilaton, so this phi field ends up being this angular, because that's how you had this decomposition also, right? Yeah.
Wait. Sorry, no, sorry. Phi here is the value of the dilaton.
Yeah, but in the 3D gravity,
Oh, I don't immediately see that. So let me just say that I agree that ultimately the energy can be associated to this deficit angle, but it's not obvious to me how to translate that to this expression. But I agree with what you said. Okay, let me get to the punchline of this part. So we have two notions of energy now, and so remember, m was phi squared minus d phi squared. D phi squared I can express in terms of I can write it as d n tilde phi squared minus d n tilde or the n tilde or perpendicular, namely the derivative along the boundary, or along the constant r slice rather. And if you write it in this way, you will notice that the Brown-York energy renormalized can be expressed in terms of m in the following way: phi squared 1 minus square root 1 minus m phi minus 2 plus d and perpendicular phi squared. So we get this expression, which so it looks almost like the TTbar form, except for this pesky term. However, you can easily remove this by basically by picking a gauge where phi defines for you the radial coordinate. And so you can get rid of this term. Or said differently, the value of phi along the the value of phi is conserved along the boundary. That's another way of saying it. So it's just that phi is just a function of r.
I didn't understand all the derivations, but let me just make sure I understand the formula.
Yeah.
M here is the ADM mass. Is this right? Mass measured at infinity.
It coincides with the mass measured at infinity, correct.
Okay, and this renormalized Brown-York is some sort of local mass that you're trying to associate at some radial distance?
Correct.
And the definition of this thing is that you work with respect to a local time that is normalized like dt squared at that point, like a proper energy.
Exactly. But you first need to be careful that notion of t coincides with the boundary physical time.
Fine. Okay, I get it.
Yes.
Thank you.
Yes.
So it's like a redshifted kind of thing.
It involves that, correct? Yes. If you look at this expression, we are able to answer the question from the beginning of this section, that it tells us that it identifies m with E naught and phi squared with 1 over lambda. Okay, that's the takeaway from this part. Let me just emphasize that although m, yes, so it coincides with the ADM mass, yet it was something that was computed, quote unquote, locally, right? It's expressed as a function of phi squared minus d phi squared. And that combination is constant throughout the bulk, basically. Okay, so now that we identified the parameters, now let's talk about the setting up the gravity path integral. Okay. All right. So we imagine that we want to define a gravity path integral with those with boundary conditions fixing m and phi squared, because again, we're trying to do what we did on the boundary. We fix the seat energy and lambda. And let's imagine we define a theory on S1, the boundary S1, where we impose m is equal to phi squared minus dn tilde phi squared and phi, which let's parameterize phi as square root m times cosh RC. This is something that I can do. And then, given these boundary conditions, let me look for solutions. And the solution that I find is gamma tt is equal to m sine hyperbolic squared r, and I guess phi, and phi is equal to square root m times cosh r. This is for r less than rc, right? RC is where the boundary is. Let me say what I am not doing. I am not defining a gravity path integral where I, or rather, yeah, I'm not imposing that, the volume, let's say, in the bulk of going from this point to this point is finite. All I am imposing is that the value of phi on the boundary is finite. The saddle point that I find is one where there's a finite amount of space within that circle. Okay, let me, yeah. Okay. All right. Now imagine
sorry, you're trying to define a gravity path integral at finite distance, right?
No. I'm defining a gravity path integral with this value of phi being finite. So usually this phi corresponds, it's the area of the transverse space. Usually in ADS-CFT, in ADS-CFT, that usually blows up near the boundary. Yes. So if that's what you mean, if that's what you mean by defining gravity path integral in finite space, then yes.
Yeah. So in particular, one way to define it would be to specify an induced metric or something like that on the boundary.
Mm-hmm.
And that's more or less what you're doing, right? Because you're not allowing things to vary in theta. So the only information about the theta direction is that the length, which is phi.
Mm-hmm.
And then what about the remaining two dimensions? Are you specifying that somehow?
I am not. So notice that I'm specifying phi and m. So I'm not treating the metric symmetrically.
Okay. So it's like Dirichlet boundary conditions for this direction and Neumann for the other one.
Roughly speaking. Roughly speaking.
Okay.
Good. And okay. So now, so you can ask, what is this space-time what is the interpretation of the solution? Well, if you take this, if you take the solution and you continue this t, maybe I should call this tau. If you continue tau to it, then the solution you get is just the this thing is just a cigar, and so this thing just gives you the eternal black hole space-time. So I'm starting from this slice, which is this slice, and I'm continuing t to it, and that gives me this boundary is some finite location here in the bulk. Okay, that's what this corresponds to. The origin here is the bifurcation surface there. Okay. there's a small puzzle. So this is all standard, but now there's a puzzle, namely m is phi, well, I don't need to write it again. So just look here. M is phi squared minus dn phi all squared. So it seems like there is a, it seems like there exists a phi minimum, which is square root m. Let me write it here. I mean, this minimum is clear from this parameterization, but I don't have to use this parameterization. Suppose I just take by hand, I take phi to be less than square root m. What goes wrong? Well, otherwise you get this complex. Well, the only way you can satisfy those equations is that d phi is imaginary. This is related to the complexification of energies. Because essentially the dn phi term is the thing that is responsible for the square root term. And the argument of the square root becoming negative is analogous to the dn phi becoming imaginary. Okay, but we want to avoid this. So what's the analog of shifting the flow that we did on the boundary, adding this cosmological constant term, etc.? Well, here, the reason why we got this complex energy, rather we couldn't find these real, let's say, real solutions for small enough phi, is because we implicitly assumed that n squared, or I guess n tilde is what I've been calling it, to be spacelike. This is the normal to the boundary. What we're going to do now is we're going to allow n tilde squared to be time-like. So we're going to look for solutions of this form. And if you do this, then the formula for m gets modified slightly, namely the derivative term of respect to phi changes sign. And if you then look at the Brown-York energy through normalized, express it in terms of this m, you get the following equation. So there's two things to say here. One is that we continued phi to be less than this square root m, which is the analog of lambda critical, or 1 over lambda critical, roughly. And by changing this condition on the normal, which changed the expression for m and ultimately led to a new formula for the Brown-York energy, which agrees with the TTbar plus 1 over lambda squared deformed energies. So we found the modification in the bulk that we had to do that reproduced the deformed energies past lambda critical. Okay, but now let's talk about what the solution looks like. So again, the solution is we have a circle, we have an S1, and we define m and phi. Now we can parameterize phi as square root m cosine RC, R cutoff. The solution for the metric, given these boundary conditions, is minus dr squared plus m sine squared r dt squared, which is just negative of the Sitter space, ds2. Okay, but what does this solution correspond to from the bulk perspective, from the black hole perspective? Well, so let's do what we did last time. Let's take a slice of this solution and continue it, and continue the t, or tau to it, or t to I tau. Well, so let me first draw the full Penrose diagram for the eternal black hole. I claim that the following identification is well, damn it. The following identifications should be made. That this line corresponds to a line here. This S1 here, this circle, when you continue it to Lorentzian time, gives you the union of these two blue lines. And the origin of this disk is the bifurcation surface here. And
you've done an angular right?
Good. Right now, J is equal to 0. You're going to tell me that this is the wrong spacetime to consider. And I agree with you. And not only do I agree with you, but the formulas agree with you. Because if you take, so you can ask, how far, well, maybe let me just say it in words. How far can I push this blue slice in? Okay. How far can I, how small can I make phi, basically? Well, the smallest you can make phi is 0. That's like taking lambda goes to infinity, because remember, phi squared is like 1 over lambda. And then you can ask, where is the lambda goes to infinity surface in this eternal black hole geometry, in this Lorentzian eternal black hole geometry? Well, that surface is actually here. So you cannot flow past the green line. The blue line just asymptotes to this green line. So you have some fixed point of the flow. Okay, and we know from the three-dimensional perspective, that's where you should cap off the space-time, right? Because that's where you have the singularity. So this part of the space-time is actually not there. So secretly, the right picture here for what the quote-unquote solution looks like in this region is actually something like this, where the squiggly line is meant to represent the R equals 0 conical singularity of J equals 0 BTZ. Okay, so this quote-unquote thermal disk, if you will, the analog of the cigar ends at this squiggly line where the singularity is. Let me just quickly say what happens when J is not equal to 0.
I have one question.
Let me just say this, and then I'll take a question because I need to leave in like 15 minutes. Sorry. So yeah. So if you take J to be not equal to 0, then we do know that you should get that the full space-time should be there modulo this possible instability of the inner horizon. Let me ignore that. Then in that case, we have 3 flows. So there's this flow going from the outside to the horizon. Okay. Then there is the flow that takes you into the interior, which covers this region. But you can keep going and do the same trick where you, flow to the inner horizon, and then you peel off the inner horizon in the but in the interior. So you have something like that. And from the perspective of these solutions of the, well, from these S1 boundary perspectives, we started with this for the exterior. Then in the interior, we also had something, well, it's still, the topology was still a disk. But once you get to this last stage in the deep interior, after changing the third sequence of the flow, then you get a spacetime that looks like this. So this is the S1 where you put the boundary conditions, and the spacetime is quote unquote on the other side. And this is, oops. And this is the R equals 0 surface. And again, this matches onto the fixed point of the flow. Fixed point of the J not equal to 0 flow. Yeah, so the upshot again is that when you define the gravity path integral with these boundary conditions, and you look for these the solutions, they correspond to these continuations of different patches of the eternal black hole geometry, and the fixed point of the flow corresponds to the finite boundary asymptoting to the location of the singularity. In the case where angular momentum was 0, that was at the spacelike conical singularity. But for J not equal to 0, you are able to go past it and go all the way past the inner horizon and get arbitrarily close to the time-like singularity of rotating BTZ. And two final comments. One is that we can actually, so we haven't actually done this yet, but it is possible to compute TTbar flowed correlation functions of the stress tensor, and that would presumably directly probe the singularity. So that's a calculation in progress. I guess one other thing is these gravity path integrals with these non-standard boundary conditions, I think, is a bit understudied and worth thinking about more. So let me end there, and let me take your question, Abhijit, first.
Yeah, sorry, I just have a basic understanding question. So is it the case that what you were talking about just now was about what happens, how you would describe the flow after that, after the lambda c, where you turned on this different type of flow? That's what you were explaining here, right? For some value, some choice of E naught.
Yes.
Okay, now if I choose that E naught to be, of order central charge, but still lighter than the black hole, then why is it that one is talking about the black hole here necessarily? I mean, you could have not chosen to be much below the threshold also.
Yes, no, that's a good point. Let's see. I feel like that same question can be applied to the standard TTbar story, right? Like
well, in that case, I guess things are described in terms of not necessarily horizons and so on, but rather just a conical geometry. The way I understood it, maybe it's wrong, but I thought it was just a conical geometry, but moved inside.
But what corresponds to the where do the energies complexify? Is it when you hit the conical singularity, or is it somewhere else?
Yeah, so that I wouldn't know. So I guess one could ask that. What does complexification mean? In particular, there is no central charge appearing in anywhere in this energy relations and so on. The energy, how it deforms. So then I was just wondering how one gets a different story for black holes compared to the other things.
Yeah, no, that's a good question. I would have to get back to you on that.
Thank you. Questions?
Sorry, Ahmed, one quick one. There's the story that Aaron Wall was trying to develop at some point about trying to interpret TTbar as being taking the boundary into a space-like slice in the bulk. If I understand, if I remember right, that was just an ordinary ADS. Do you know what I'm talking about?
Yes.
I was wondering whether there was a relationship. It felt sort of a little bit similar.
I feel like, I feel like there must be some kind of relationship, but the way that we put boundary theories on space-like slices seems different. Like they consider some Euclidean path integral, and you imagine defining some TTbar prescription that moves the boundary in while keeping it anchored here and here, keeping it anchored here and here.
Right.
Something like that, which is kind of different from what I'm doing. I'm doing, like, morally speaking, from like like suppose you start with the thermal partition function, or rather just the path integral on the S1. In some sense, what I'm doing is I'm evolving the entire boundary in like that, and once I get to the center, I evolve it somehow. It looks like it disappears in this picture, but then it's now in the interior somehow.
Okay. So you say the main difference is that it's your boundaries are not wedged at the actual boundary at all, whereas his was.
Correct. That's one main difference. Yes.
Any more questions?
One quick question. Ahmed, can you think of, is there some utility to thinking about this deformation directly from the matrix model point of view, dual to JT gravity? I mean, avatar of this TTbar deformation, or the change in the flow and so on, directly from the matrix model point of view.
Well, one thing you can ask, and we might have some words on this in the paper, that like maybe there's a way of running that whole program of interpreting, well, what's the interpretation of the wormholes connecting multiple copies of these interior circles? You can ask that kind of question. So is it what? So we know that at least in the exterior, you can use that to study the spectral form factor and so on, and look at properties of the distribution of energies. And so what would that correspond to in the case where now we're talking about the interior circles? There's a chance that it might not add anything else, but yeah, it's the only comment I can make.
Okay, thank you.
Okay, if there are no further questions, let's thank Ahmed again.